Hello. Today we are going to discuss about the kinetic theory of gases. Firstly, we have to discuss the term matter, which obviously means anything which occupies space and has a mass is called as the matter, and it is composed of molecules. Now, the kinetic theory that we are going to deal with in this segment is it tells us that the molecules that form the matter, they are obviously they are the smallest constituent of matter which can exist freely in nature, and they are constantly in motion, and the heat contained in the body is in the form of molecular motion. The molecules of a body attract each other with a certain force. The type of motion of molecules and the force of attraction between them is different in different states of matter. As we know, the different states of matter that we have the solids, we have the liquids, and the gases. Now, these undergo various properties. Uh, the the kinetic theory of matter, uh, the conception of kinetic theory of matter uh, is the various properties of matter can be explained, and the properties being that of expansion and melting, also the case of boiling. These various properties can be explained in terms of the kinetic theory. Evaporation, diffusion, all of these. Now, next up, before going into the details of what we are going to discuss, we must bring in the term called as the ideal gas. Now, what do you mean by ideal gas? Anything ideal is not something which is available to us. Now, the same goes with the case of ideal gas. It is one where the which has a zero size of molecule and also zero force of interaction between the molecules. That is obviously not really possible. We must have the molecule must have some size, and it must be having some force of interaction between them. They must be having, or else they won't constitute a system. Now, these concepts, however, nearly hold good if we are considering a gas of consisting of point masses which are separated by very large distances. So, if we have point masses separated by very large distances, then they will be somewhat nearly close to the ideal behavior, and this is uh, possible in case of low pressure and at high temperatures. Now, at low pressure, the molecules tend to remain away from one another at large distances. So is the case of high temperature. The molecules tend to remain at far off distances from one another. Now, the reverse of this, that is when the pressure becomes higher or increases and the temperature decreases, the molecules tend to come close to one another and they divert away from the ideal behavior. and as a result of that they will finally enter into the liquid region and ultimately to the solid state. Now the ideal gas associates with itself an equation which is known as the ideal gas equation. This is the equation for a perfect gas. There should be no force between any of its molecules, which forms the basic postulate of the kinetic theory of gases. And so the gas is set at low pressure and at high temperatures, thereby having its molecules really far away from one another. So let's see the equation of state for an ideal or perfect gas, or the ideal gas equation. Now in that case, let's consider a system. For that, we firstly take uh, an airtight piston arrangement which is having a certain weight on it, and the pressure that is built in that gaseous system which is present inside of it, which is at a temperature T1 right now. The pressure is P1 and the volume is V1. These are the initial parameters that are involved in that system. Now in case we further uh, increase the temperature, let us say, so we go from this to this case where the temperature has been changed to T2, and as a result of that there has been a change in volume now, and let that volume supposedly be small v as for now. The pressure is, however, maintained constant. These are the weights that are placed on the piston. So it's probably connected to some external agent which is helping in the motion. Now this pressure, however, is maintained at P1. Now we will be studying in detail about Charles' law, but here the temperature has been changed from T1 to T2. As a result of that, the volume has changed from V1 to V, and from Charles' law we have V1 by T is equal to constant. So V by T is equal to constant, that is V1 by T1 will be equal to V by T2, and from that we can have V1 by V to be equal to T1 by T2. Now that's okay. Now we change the pressure further. Suppose we add weights to it, then now that changes the pressure. The container hasn't become thin, it's just the space that is available in which I'm restricting myself to. So it's the same container, so don't be confused with that. And now we have the pressure increased. We are adding weights over there, which is changing the pressure to P2. We are maintaining, however, the temperature to T2, but the volume is changing. The volume now has become V2. So V2 is the new volume, the final volume, that is. So from Boyle's law, we have P1 V to be equal to P2 V2. And from equation 1, as we have it, let this be equation 1 and this be equation 2. And from equation 1, what we have is, we have the value of this V. We substitute this value of V from that equation 1. What do we have? P1, and for V over there is T2 by T1 times of V1, T2 by T1 times of V1, and here we have P2 V2. Well, we can just take the P2 down and we end up with P1 V1 by T1 to be equal to P2 V2 divided by T2, and this obviously means that PV by T is equal to constant, and this is the case of ideal gas equation, and the constant on the right hand side is the ideal gas constant. The gas constant has a value, and we'll be obtaining that. It's equation 3. If This is equation 3, and if we are applying that to 1 gram molecule or 1 mole of a gas, then the constant that comes up is known as the universal gas constant. 1 gram molecule or 1 mole of gas occupies 22.4 liters at normal temperature pressure, and so the value of R that we get over there is that is for 1 mole is 8.3. So this constant is R, that is a universal gas constant, universal gas constant, and that has a value for normal temperature pressure, that is pressure maintained at 76 centimeters of mercury, and the acceleration due to gravity obviously is 9.8 considered. Volume is 22.4 liters or 0.0224 meter cube, and temperature is 273 Kelvin. So in that case we have the value of R, and that is equal to 8.311, the unit being joule per mole per Kelvin. That's the value. And this is for 1 mole, and for n moles it will be n times of R. This is for 1 mole, and for n moles we'll have nR on the right hand side, PV by T on the left hand side, resulting in PV is equal to nRT, the ideal gas equation for n number of moles. And as we know, for a given mass of a gas, let's say m, the number of moles is small n, which is equal to the small m divided by the capital M being the molar mass. So we can substitute this over there, and what we are going to end up with is that PV is equal to m over the molar mass times of RT, and if m is equal to that small m, if supposedly is equal to 1 grams, then what we are going to get is PV will be equal to RT divided by M, and that R by M term is known as the specific gas constant, which is small r. R is equal to R by M, that is the specific gas constant. Now if we wish to get back to reality, we have the real gas. The real gases are they're not the gases are not actually ideal, so they have the behavior. The hydrogen gas, however, has nearly the behavior of an ideal gas. So whenever we consider the ideal gas, we can consider the case of hydrogen. But as for the as I mentioned, reality check, we have the real gases, which are determined by the van der Waals equation. He came up with the equation of state for real gas, and that was of the form P plus A by V squared. V here is the volume, the same as the previous case. V minus B times of RT for a unit for a single mole, that is N is equal to 1. So this is the real gas equation, which has the PV terms, but P and V, they have constants associated with them, where A and B are the van der Waals constant. Now the ideal gas cannot be applied to a system of say saturated vapors. So in case of then in case of a mixture of gas and saturated vapors, we end up with a partial pressure term, which will be discussed later. So this is the case of real gas, the real gas equation, van der Waals equation for real gases. And now we can discuss the gas laws. First up, we have, in case of gas laws that we are to discuss, first up we have the Boyle's law, which states that it deals with the variation of the pressure with volume of a gas when the temperature is kept constant. So it states that the pressure times of volume is constant. This is the result of the equation. Actually, the pressure is inversely proportional to the volume when we have kept the temperature as constant. Now, the behavior of an ideal gas can be plotted graphically as this. If we are considering the variation of PV with respect to V, then it will be a straight line because PV is constant. That is what we have got over here. And in case we want to check the variation of P with respect to V, now remember it is inversely proportional. So if we are checking the variation with respect to B, the graph will be of this form, the inverse graph. And if we are considering the variation of P with respect to 1 by V, obviously it is directly proportional to that, and that means the behavior will be like this. It will be a straight line graph. Now this is for the ideal gas. Now if we consider the real gas, the real gas does obey Boyle's law, but only at the Boyle's temperature, whose value depends on the nature of the gas. Then up next we have the Charles law. As discussed earlier, it's the volume by temperature at a given pressure, that is at a constant pressure, that is equal to constant, or we have V proportional to T. And if we were to do the graphical analysis, it's almost the same case, except for the as per the formula we have the variation to be like this: temperature and volume going in the straight line, and the reciprocal of temperature with the volume going inversely. Now if we have as per the Charles law is concerned, at absolute temperature, let's consider the volume to be equal to V naught, and so this is the absolute temperature where the volume is V naught, and some other temperature we have the volume to be equal to V. So we can relate them as V by V naught will be equal to T by T naught. And we can have V to be equal to V naught times of, now T is any temperature which is T above 273, and the absolute temperature is obviously equal to 273, and from this we have V naught multiplied with 1 plus T by 273 is the value of V. And from that what we get is 1 V minus V naught. If we take it to the other side and divide the factor by V naught by 3, we are going to end up with T by 273, not T by 273, actually 1 by 273. And that 1 by 273 is the volume coefficient of gas at constant pressure, usually represented by gamma p. Volume coefficient of gas, which is at constant pressure, is defined as the change in volume per unit degree rise of temperature. Now I'll have to end it over here. We'll be discussing few more gas laws, followed by the kinetic theory of gases, the postulates and the equations related to that in the upcoming videos in this series. Till then, thank you for watching.